All right, and welcome to part two of our lecture on chapter 11. And we're going to start with reactions in solution. So we now turn specifically to reactions in solution, where the reactant molecules do not fly freely through gaseous medium and collide with each other, but wriggle past closely packed neighbors as gaps open up in the structure of the liquid. Activation control and diffusion control. So the concept of the rate-limiting step plays an important role for reactions in solution, where it leads to the distinction between diffusion control and activation control. To develop this point, let's suppose that a reaction between two solute molecules A and B occur by the following mechanism. First, we assume that A and B drift into each other's vicinity by the process of diffusion and form an encounter pair, AB, at a rate proportional to each of their concentrations, where A plus B lead to AB. And the rate of formation of this AB encounter pair will be equal to the rate constant K times of this interaction times the concentration of A times the concentration of B. Now, the D subscript for this rate constant reminds us that this process is diffusional. The encounter pair may persist for some time as a result of the cage effect, the trapping of A and B near each other by their inability to escape rapidly through the surrounding solvent molecules. However, the encounter pair can break up when A and B have the opportunity to diffuse apart, so we must allow for the following process, where the encounter pair AB dissociate to A plus B, with a corresponding rate of loss of AB equal to K prime times the concentration of AB. We suppose this process is first order in AB. Competing with this process is the reaction between A and B while they exist in an encounter pair. This process depends on the ability to acquire sufficient energy to react. That energy might come from the jostling of the thermal motion of the solvent molecules. We assume that this step is first order in AB, but if the solvent molecules are involved, it's more accurate to regard it as a pseudo-first order with the solvent molecules in great and constant excess. In any event, we can suppose the reaction is the encounter pair AB goes to products, where the rate of reactive loss of AB equals the rate constant K sub A times AB, where A subscript reminds us that this process is activated in a sense, but it depends on the acquisition of AB of at least a minimum amount of energy. Now we use the steady state approximation to set up the rate law for the formation of products. As shown in derivation 11.5 in the text, if you're interested in pursuing that derivation, we find the following, where the rate of formation of products equals the rate constant R, K sub R, times concentration of A times the concentration of B, where K sub R equals K sub RA times K sub RD divided by K sub RA plus K sub RD prime. Now we distinguish two limits. Suppose the rate of reaction is much faster than the rate at which the encounter pair breaks up. In this case, K sub R sub A is much greater than K sub R D prime, and we can neglect the second in the denominator of the expression for K sub R. The K sub RA in the numerator and denominator then cancel, and we're left with the following. The rate of formation of products equals K sub RD times the concentration of A times the concentration of B. In this diffusion-controlled limit, the rate of reaction is controlled by the rate at which the reactants diffuse together, as expressed by K sub RD. For once they have encountered the reaction so fast, they'll certainly go to form products rather than diffuse apart before reacting. Now, alternatively, we may suppose that the rate at which the encounter pair accumulates enough energy to react is so low that it's highly likely the pair will break up. In this case, we can set K sub Ra to be much lower than K sub Rd prime in the expression for K sub R and obtain the following, where the rate of formation of products equals K sub A times K sub D divided by K sub D prime times the quantities for concentration of A and B. In this activation-controlled limit, the reaction rate depends on the rate at which the energy accumulates in the encounter pair as expressed by K sub Ra. A lesson to learn from this analysis is that the concept of the rate-determining stage is rather subtle. In the diffusion-controlled limit, the condition for the encounter rate to be rate-determining is not that it's the slowest step, but that the reaction rate of the encounter pair is much greater than the rate at which the pair breaks up. In the activation-controlled limit, the condition for the rate of energy accumulation to be the rate-determining step is likewise a competition between the rate of reaction of the pair and the rate at which it breaks up, and all three rate constants control the overall rate. The best way to analyze competing rates is to do as we've done here, to set up the overall rate law, then to analyze how it simplifies as we allow particular elemental processes to dominate others. A detailed analysis of the rates of diffusion of molecules in liquids show that the rate constant, K sub Rd, is related to the coefficient of viscosity, eta, and the medium by the following, where we have 8RT divided by 3 eta, which is our coefficient of viscosity. We see that the higher the viscosity, then the smaller the diffusional rate limit constant, and therefore the slower the rate of diffusion-controlled reaction. So this is a good way to transition into the discussion around diffusion. Diffusion plays such a central role in the processes involved in reactions and solutions that we need to examine it more closely. The picture to hold in mind is that a molecule in a liquid is surrounded by other molecules and can move only a fraction of a diameter perhaps because its neighbors move aside momentarily before colliding. Molecular motion in liquids is a series of short steps with incessantly changing directions, like people in an aimless, milling crowd. The process of migration by means of a random jostling motion through a fluid, a gas as well as a liquid, is called diffusion. We can think of the motion of molecules as certain short jumps in random directions, a so-called random walk. If there's an initial concentration gradient in the liquid, for instance, a solution may have a high concentration of solute in one region, then the rate at which the molecules spread out is proportional to the concentration gradient, and we can write that the rate of diffusion is proportional to the concentration gradient. To express this relation mathematically, we introduce flux, J, which is the number of particles passing through an imaginary window in a given time interval, divided by the area of the window and the duration of the interval. So it's a number of things moving through a certain unit area per unit time. So given that, we can say that flux equals the number of particles passing through a window divided by the area of the window and divided by the time interval. Then, in this case, flux equals negative d times the concentration gradient, which we have in 1118b here. So equation 1118b is called Fick's first law of diffusion. The coefficient d, which has the dimensions of area divided by time with meters squared per second, is called the diffusional coefficient. If d, the diffusional coefficient, is large, molecules diffuse rapidly. Some values are given in table 11.1 in the text if you're interested in pursuing that. The negative sign in equation 1118b simply means that if the concentration gradient is negative, then the flux is positive. To get the number of molecules passing through a given window in a given time interval, we multiply the flux of the area of the window and the time interval. If the concentration in equation 18b is a molar concentration, then the flux is expressed in moles rather than number of molecules. So let's take a look at figure 11.9 here. the flux of solute particles is proportional to the concentration gradient. Here we see a solution in which the concentration falls from left to right, as depicted by the shaded band of the curve. The gradient is negative, down from left to right, and the flux is positive towards the right. The greatest flux is found where the gradient is steepest, towards the left. The diffusion of molecules may be assisted, and normally greatly dominated, by bulk motion of the fluid as a whole, like when the wind blows in an atmosphere and current flows in lakes. This motion is called convection. Because diffusion is so slow, we speed up the spread of solute molecules by inducing convection by stirring a fluid, turning on an extraction fan, or relying on natural phenomena such as wind and storms. One of the most important equations in the physical chemistry of fluids is the diffusion equation, which enables us to predict the rate at which the concentration of a sharp change in a non-uniform solution. In essence, the diffusion equation expresses the fact that wrinkles in the concentration tend to disperse. The formal, but still verbal, statement of the diffusion equation, which is also known as Fick's second law of diffusion, is the rate of change of concentration in a region equals d times the curvature of the concentration in the region. The curvature is a measure of the wrinkliness of the concentration. The derivation of this expression is given further in the text, which you can access if you're interested, but it shows how to derive Fick's first law. The concentration on the left and right of this equation may be either the number concentration, molecules per cubic meter, for instance, or molar concentration. The diffusion equation tells us the following. If the concentration is uniform, or its profile has a constant slope, there is no net change in concentration to the region. In this case, the rate of influx through one wall of the region is equal to the rate of efflux through the opposite wall. Only if the slope of the concentration varies through the region, only if the concentration is wrinkled, is there a change in concentration. Then, under those circumstances, when the curvature is positive, for instance, a dip in figure 1110, the change in concentration is positive, the dip tends to fill. Where the curvature is negative, the change in concentration is negative, and the heap tends to spread. So if we take a look at figure 1110, if you have on the x-axis your position and then on y-axis concentration, if you have a negative curvature here, which involves a heap or a hill, for instance, that tends to spread and be mitigated as it spreads out. Whereas if you have a dip with a positive curvature, like in this, it also tends to mitigate and become less pronounced as it diffuses. Now, we can understand the nature of diffusion more deeply by considering it as the outcome of random walk, a series of steps in random directions and, in general, through random distances. Although a molecule undergoing a random walk may take many steps at a given time, it only has a small probability of being found far from its starting point, because some of the steps lead it away from the starting point, but others lead it back. The net distance traveled in a time t from the starting point is measured by the root mean squared distance, where this denotes an average value, and x is the distance from the origin. And for a random walk in one dimension, the root mean squared distance is 2 times dt, square root of the quantity. Thus, the net distance increases only as the square root of time. So for a particle to be found twice as far on average from its starting point, we must wait 4 times as long. The relation between the diffusion coefficient and the rate at which the molecules take its steps and the distance of each step is called the Einstein Smoluchowski equation, where lambda is the length of each step, found in the model, assumed to be the same for each step, and tau is the time each step takes. This equation tells us that a molecule that takes rapid long steps has a high diffusion coefficient. We can interpret tau as the average lifetime of a molecule near another molecule before it makes a sudden jump to its next position. The diffusion coefficient increases with temperature because an increase in temperature enables a molecule to escape more easily from the attractive forces exerted by its neighbors. If we suppose that the rate 1 over tau of the random walk follows an Arrhenius temperature dependence with an activation energy of E sub A, then the diffusion coefficient will follow the relationship below, where the diffusion coefficient will equal the initial diffusion coefficient times E raised to the negative activation energy divided by RT. The rate at which particles diffuse through a liquid is related to viscosity, and we should expect a high diffusion coefficient to be found for fluids that have a low viscosity. That is, we can expect that N is going to be inversely related to the diffusion coefficient, where N is the coefficient of viscosity. So, in fact, Einstein's relation states that the diffusion coefficient equals K times T over 6 pi nu A, where A is the radius of the molecule. We can follow that by substituting for D into 1122 and get the following relationship, where the coefficient of viscosity is going to equal the initial coefficient of viscosity times our E raised to the activation energy over RT. Now note the change in sign of the exponent here. Viscosity decreases as the temperature is raised. We are supposing that the strong temperature dependence of the exponential term dominates the weak linear dependence of temperature in the numerator. The temperature dependence described by equation 1124 is observed, at least over reasonably small temperature ranges. The forces acting between the molecules govern the magnitude of the activation energy, but the problem of calculating it is immensely difficult and still largely unsolved. And here we have figure 1111, which demonstrates the relationship between temperature and viscosity. And you can see here the experimental temperature dependence of viscosity on water specifically. As the temperature is increased, more molecules are able to escape from the potential wells provided by their neighbors, so the liquid becomes more fluidic. Now, let's move on to catalysis. A catalyst is a substance that accelerates a reaction but undergoes no net chemical change to itself. The catalyst lowers the activation energy of the reaction by providing an alternative path that avoids the slow rate-determining step of the N-catalyzed reaction. Catalysts can be very effective. For instance, the activation energy for the decomposition of hydrogen peroxide in solution is 76 kilojoules per mole, and the reaction is slow at room temperature, which is why we can store hydrogen peroxide in solution under our cabinets in the bathroom or kitchen. Now, when a little iodine is added, the activation energy falls to 57 kilojoules per mole, and the rate increases by a factor of 2,000-fold. Enzymes, which are biological catalysts, are very selective and can have a dramatic effect on the reactions they control. For example, the enzyme catalase reduces the activation energy for the decomposition of hydrogen peroxide to only 8 kilojoules per mole, corresponding to an acceleration of the reaction by a factor of 10 to the 15 at body temperature. At room temperature, even lower than body temperature. So, let's talk about different types of catalysts. First, homogeneous catalysts, or homogeneous catalysis. A homogeneous catalyst is a catalyst in the same phase as the reaction mixture. For example, the decomposition of hydrogen peroxide in aqueous solution is catalyzed by bromide ion or catalase. A heterogeneous catalyst is a catalyst in a different phase from the reaction mixture. For example, the hydrogenation of ethene to ethane, a gas phase reaction, is accelerated in the presence of a solid catalyst such as palladium, platinum, or nickel. The metal provides a surface upon which the reactant binds. This binding facilitates encounters between reactants and increases the rate of reaction. We examine heterogeneous catalysts in Chapter 16 and consider only homogeneous catalysts here in this chapter. Now, there's two subcategories of catalysts that we're interested in. In acid catalysis, the crucial step is the transfer of a proton to the substrate, as we see here. Acid catalysis is the primary process in keto-enol tautomerism, which we knew from organic chemistry and see examples of in biochemistry. In base catalysis, a proton is transferred from the substrate to the base, as in the hydrolysis of esters. Now, enzymes. One of the earliest descriptions of the action of enzymes is the Michaelis-Menten mechanism. The proposed mechanism with all species in an aqueous environment is as follows. Step 1, the bimolecular formation of a combination ES, enzyme substrate, is as follows, where the enzyme encounters the substrate, forming the enzyme substrate complex. And this rate of formation of ES equals the value K sub A times the concentration of enzyme times the concentration of substrate. In step 2, there's a unimolecular decomposition of the complex where the enzyme substrate complex decomposes back to the enzyme and substrate. In step 3, there's a unimolecular formation of products and the release of the enzyme from its combination with the substrate. So in this case, the enzyme substrate complex proceeds and reacts to the product, releasing the enzyme. So you have P plus E. This can be described where the rate of formation of P equals K sub B times the concentration of the enzyme substrate complex, or alternatively, the rate of consumption of the enzyme substrate complex can equal K sub B times ES. As shown in derivation 11.6 in the text, the rate law for the rate of formation of product in terms of the concentration of enzyme and substrate turns out to be the following, where the rate of formation of product equals K sub R times the concentration of enzyme initially, where K sub R equals K sub B times the concentration of substrate over the concentration of substrate plus Km, Km being the Michaelis-Menten constant, which has the dimensions of a concentration. So K sub M equals K sub A prime plus K sub B over K sub A. And the concentration of enzyme initial is the total concentration of enzyme, both bound and unbound. So according to equation 1125, which we're seeing right here, the rate of enzymolysis is first order in the added enzyme concentration, but the effective rate constant, K, depends on the concentration of substrate. We can infer from this equation that when the concentration of substrate is much lower than the Michaelis-Menten constant, the effective rate constant is equal to the following quantity. Therefore, the rate increases linearly with the concentration of substrate at low concentrations. When the concentration of substrate is substantially greater than the Michaelis-Menten constant, the effective rate constant is equal to K sub B, and the rate law in equation 25 reduces to the following, where the concentration of substrate is substantially lower than K sub M, Michaelis-Menten constant, the rate is independent of the concentration of substrate, because there's so much substrate present that it remains at effectively the same concentration even though products are being formed. Under these conditions, the rate of formation of product is a maximum, and K sub B times the concentration of total enzyme is called the maximum velocity of enzymolysis, or V sub max. So V sub max in this case equals K sub B times the concentration of enzyme available, bound and unbound. The rate determining step is step 3, because there's ample enzyme substrate complex present, because S is so abundant, and the rate is determined by the rate at which E sub S, or the enzyme substrate complex, reacts to form the product. It follows from equation 1125 and 1128 that the reaction rate, V, at a general substrate composition is related to the maximum velocity by the following, where rate equals the concentration of the substrate times V max over the concentration of the substrate plus Michaelis-Menten constant. The rate determining step, oh, excuse me, this is redundant. I just wanted to repost this so we had it in front of us so we could see it for the following discussion. This relation is illustrated in figure 1113 below. Let's take a look at it. So in 1113, we see on the y-axis we have the reaction rate. On the x-axis we have substrate concentrations. And we have different K sub m's on our different isotherms. So the variation of the rate of the enzyme catalyzed reaction with concentration of the substrate according to the Michaelis-Menten model is what's shown when the concentration of substrate S is substantially lower than K sub m. The rate is proportional to concentration. But when concentration is substantially greater than K sub m, the rate's independent of concentration of substrate. So, equation 1129 is the basis for the analysis of enzyme kinetic data by using a line-Weick-Burger plot. A graph of the inverse of rate, the reciprocal of reaction rate, against the inverse of the substrate concentration. If we take the reciprocal of both sides of equation 1129, it becomes the following. Note that this expression has the form of y equals mx plus b, where y equals 1 over v, x equals 1 over s. So we can measure velocity over a range of concentrations of substrate, and from that linear relationship or model, we can interpret the maximum velocity Vmax from the intercept, and from the slope, once we have Vmax, we can determine the Michaelis-Menten constant for that reaction. So this is displayed on figure 1114, where a line-Weick-Burger plot is used to analyze kinetic data, and you can see from the reciprocal of substrate on the x-axis and the reciprocal of the rate of reaction on the y-axis, we have an intercept, which will give us 1 over km, and an intercept, which gives us 1 over Vmax. Or alternatively, you can get 1 over Vmax from the y-intercept and then substitute it into slope and get km that way as well. Now, we can calculate further parameters from those derived from a line-Weick-Burger plot that allow us to compare the catalytic properties of different enzymes. The turnover frequency or catalytic constant of the enzyme, kcat, is the number of catalytic cycles or turnovers, because every time it's released, it's reactivated to interact again, performed by the active site in a given interval divided by the duration of that interval. This quantity has units of a first-order rate constant and, in terms of the Michaelis-Menten mechanism, is numerically equivalent to K sub b, the rate constant for the release of product from the enzyme substrate complex. It follows from the identification of kcat with Kb from equation 1128 that kcat equals Kb equals Vmax over total concentration of enzyme. The catalytic efficiency, eta, of an enzyme is the ratio of kcat to K sub m, or the turnover frequency divided by the Michaelis-Menten constant. That's defining the catalytic efficiency. The higher the value of eta, the more efficient the enzyme. We can think of the catalytic activity as the effective rate constant of the enzymatic reaction, from the Michaelis-Menten constant equaling K sub A prime plus K sub B over K sub A, and equation 1131, it follows that the catalytic efficiency equals K cat over K sub M equals the following. The efficiency reaches its maximum value of K sub A when K sub B is much greater than K sub A prime, because K sub A is the rate constant for the formation of a complex from two species that are diffusing freely in solution. The maximum efficiency is related to the maximum rate of diffusion of the enzyme and substrate in solution. In this limit, rate constants are about 10 to the 8th, 10 to the 9th cubic decimeters per mole per second for molecules as large as enzymes at room temperature. The enzyme catalase, for instance, which is highly efficient, has a catalytic efficiency of 4.0 times 10 to the 8th cubic decimeters per mole per second, and is said to have attained catalytic perfection in the sense that the rate of reaction it catalyzes is controlled only by the diffusion. It acts as soon as the substrate makes contact. This correlates in meaningful sense, outside of the parameters of this text, to a single enzyme of catalase under biological conditions being capable of reacting with 300,000 peroxide molecules per second. The action of an enzyme may be partially suppressed by the presence of a foreign substance, which is called an inhibitor. An inhibitor may be a poison that's been administered to the organism, or it may be a substance that is naturally present in a cell and involved in its regulatory mechanism. In competitive inhibition, the inhibitor competes for the active site and reduces the ability of the enzyme to bind the substrate, which is what we see in 1116 below. In non-competitive inhibition, the inhibitor attaches to another part of the enzyme molecule, thereby distorting it and reducing its ability to bind the substrate by modifying its tertiary structure and modifying the active site so that it can no longer interact with the substrate effectively. Now, here we have an example of determining catalytic efficiency of an enzyme, and I think this is worthwhile. Go ahead and pause the screen here. Work your way through this example, and although we're not going to have you plotting this de novo, and it gives you a plot to visualize, it should help you with understanding a little bit how you would make a Lineweaver brick plot and determine catalytic efficiency from raw data. And once you've done this, let's go ahead and move on to the next slide, where we're going to talk about chain reactions. Now, many gas phase reactions and liquid phase polymerization reactions are chain reactions, reactions which an intermediate produced in one step generates a reactive intermediate in a subsequent step, then that intermediate generates another reactive intermediate, and so on. The structure of chain reactions. The intermediates responsible for the propagation of a chain reaction are called chain carriers. In a radical chain reaction, the chain carriers are radicals. Ions may also propagate chains, and in nuclear fission, the chain carriers are neutrons. The first chain carriers are formed in the initiation step of the reaction. For example, chlorine atoms are formed by the dissociation of chlorine gas molecules, either as a result of vigorous intermolecular collision in a thermolysis reaction or as a result of absorption of a photon in a photolysis reaction. The chain carriers produced in the initiation step attack other reactant molecules in the propagation steps, and each attack gives rise to a new chain carrier. An example is the attack of a methyl radical on ethane, where we have our methane radical interact with ethane. This results in the formation of methane plus an ethane radical. The single dot signifies the unpaired electron and marks the radical, which in this section we need to emphasize. In some cases, the attack results in the production of more than one chain carrier. An example of such a branching step is oxygen radical plus water, leading to the formation of a hydroxyl radical pair. When the attack of one oxygen atom on an H2O molecule forms two hydroxyl radicals. The chain carrier might attack a product molecule formed earlier in this reaction. Because this attack decreases the net rate of formation of product, it's called a retardation step. For example, in a light-initiated reaction in which HBr is formed from H2 and Br2, an hydrogen atom might attack a hydrobromic acid molecule leading to H2 and Br, as shown below here. Or we have our hydrogen radical interacting with HBr, leading to the formation of a bromine radical. The retardation does not end the chain because one radical gives rise to another, but it does deplete the concentration of the product. Elementary reactions in which radicals combine and end the chain are termination steps, where you have two radicals coming together to form a stable product that no longer participates in radical-based propagation of the reaction. In this case, or this example here, we have two ethane radicals, and they come together forming butane because each of the unpaired electrons can join together, forming a bonding pair of electrons. Now, in an inhibition step, radicals are removed other than by chain termination, such as by reaction with walls of the vessel or with foreign radicals. So, in this case, ethane radical can interact with some other random radical R, and in this particular case, the NO molecule has an unpaired electron that is a very efficient chain inhibitor. So the observation that a gas phase reaction is quenched when NO is introduced is a good indication that a radical chain mechanism is actually the mechanism of operation. So let's talk about radical propagation or chain reactions in the context of explosions. And I like to tell people that, at least in the context of organic chemistry, but many other chemistries as well, in my experience, a majority of chemistry students decide to take up chemistry for one of two common interests. One, drugs. Two, explosions. And so let's talk about the second, explosions. And you'll have to guess which of those two is my favorite. A thermal explosion is due to the rapid increase of a reaction rate with temperature. If the energy released in an exothermic reaction cannot escape, the temperature of the reaction system rises, and the reaction goes faster. The acceleration of the rate results in a faster rise in temperature, and so the reaction goes even faster, catastrophically fast. A chain branching explosion may occur when there are chain branching steps in a reaction, for the number of chain carriers grows exponentially, and the rate of reaction may cascade into an explosion. An example of both types of explosion is provided by the reaction between hydrogen and oxygen, where you have two equivalents of hydrogen gas reacting with an equivalent of oxygen gas to form two equivalents of gas-state water. Although the net reaction is very simple, the mechanism is very complex and has yet not fully been elucidated. It's known that a chain reaction is involved and that the chain carriers include hydrogen radicals, oxygen radicals, hydroxyl radicals, and water radicals. Some steps include an initiation, where hydrogen gas plus oxygen gas radicals react to form a pair of hydroxyl radicals, and propagation steps, which are shown below here, including two branching steps. The two branching steps can lead to a chain branching explosion specifically. The occurrence of an explosion depends on the temperature and pressure of the system, and the explosions region for the reaction are shown in the illustration in the top right corner here. At very low pressures, the system is outside the explosion region and the mixture reacts smoothly. At these pressures, the chain carriers produced in the branching steps can reach the walls of the container where they combine with an efficiency that depends on the composition of the walls. Increasing the pressure of the mixture along the broken line in the illustration takes the system through the lower explosion limit. The mixture then explodes because the chain carriers react before reaching the walls, and the branching reactions are explosively efficient. The reaction is smooth when the pressure is above the upper explosion limit. The concentration of molecules in the gas is then so great that the radicals produced in the branching reaction combine in the body of the gas, and the gas phase reactions can occur. Combination reactions like this are facilitated by three-body collisions because the third body, M, can remove the excess energy and allow the formation as a bond. Now, this is particularly interesting because one of my absolute favorite demonstrations is typically done in a general chemistry environment where we actually explode hydrogen and oxygen gas, and we use it as a mechanism of demonstrating the power of oxidation, where you have three balloons, one with just hydrogen, one with just oxygen, and one with both hydrogen and oxygen mixed. And if you put a flame on the end of a meter stick underneath the balloon with just oxygen, the flame grows because it's being fed oxygen as the balloon bursts. And then you do it to hydrogen and it's a fireball. It's very dramatic. But it doesn't have oxidizer inside the balloon, and the oxygen from the atmosphere has to work its way in, so you get this very, very impressive fireball, but nothing that shocks you. And then, thirdly, you do the hydrogen-oxygen mix. And just a simple balloon mixed with hydrogen and oxygen touched off by a flame will physically shake a lecture hall. It's concussive. And that is literally this sequence of chain reactions that are radical-based. So although we're demonstrating this particular reaction in general chemistry as a demonstration of the action of an oxidizer, in reality, we're demonstrating a fundamental explosion that's operating through a rapidly accelerated radical-based mechanism. So, 1.3 slides left, and we are done with rates of reaction for this particular course. So hold on tight, we're almost there. The rate laws of chain reactions. A chain reaction often leads to a complicated rate law, but not always. As a first example, consider the thermal reaction of hydrogen gas with bromine. The overall reaction and the observed rate law are as follows. Here and here. Note the complexity of the rate law. The complexity of the rate law suggests that a complicated mechanism is involved. The following radical chain mechanism has been proposed, where you have an initiation, where Br2 is split to a pair of bromine radicals, and propagation steps, where the bromine radical interacts with hydrogen, splitting it to form hydrobromic acid plus a hydrogen radical, and then a hydrogen radical can interact with bromine, generating hydrobromic acid plus another bromine radical. In this and the following steps, rate, V, either means the rate of formation of one of the products or the rate of consumption of one of the reactants. We'll see specifically the species only if the rates differ. So, step 3, our retardation, can occur if we consume hydrobromic acid, the product, with a hydrogen radical, and it can be terminated through the interaction of multiple radicals, where a bromine radical interacts with another bromine radical to form bromine gas at the wall. So, the third body, M, a molecule of inert gas, removes the energy of recombination. The constant concentration of M has been absorbed into the rate constant, K sub D. Other possible termination steps include the recombination of hydrogen atoms to form H2 and the combination of H and Br atoms. However, it turns out that only Br bromine atoms recombination is important in this context of the mechanism. Now we establish the rate law for the reaction. The experimental rate law is expressed in terms of the rate of formation of product, HBr, so we start by writing an expression for its net rate of formation. Because HBr is formed in step 2 by both reactions and consumed in step 3, we see the following. The net rate of formation of HBr is a term which takes all three of these processes into account, 2 of formation and 1 of removal. To make progress, we need the concentrations of the intermediates, bromine and hydrogen. Therefore, we set up the expressions for their net rate of formation and apply the steady state assumption to both. So, firstly, we have a net rate of formation of hydrogen and then a net rate of formation of bromine, both set to 0. The steady state concentration of the intermediates are found by solving these two equations and are as follows. When we substitute these concentrations into equation 1134, we obtain a rate of formation of hydrobromic acid, which looks like this relatively complex rate expression. This equation has the same form as the empirical rate law noted, and we can identify the two empirical rate coefficients as the following. We can conclude that the proposed mechanism is at least consistent with the observed rate law. Additional support for the mechanism would come from the detection of the proposed intermediates by spectroscopy and the measurement of individual rate constants for the elementary steps and confirming that they correctly reproduced the observed composite rate constants. So that is it for this chapter. I'm going to upload this video, and then we're going to do one more chapter, which we'll be looking, which we'll get to next. But in the meantime, go ahead and process this, and I'll be seeing all of you shortly in another day or two.